This is linear algebra, lecture 5, and we finished the preliminary part of the course. Preliminary. Yeah, let me spell it right. So this is sort of the warm-up. The warm-up in linear algebra are linear equations and matrices, and the main subject of the course has to do with vector spaces and linear transformations. And the chapter on this, which I think is chapter 3, is posted on Blackboard in course material. The main example of a vector space and the most important example is Rn, which is the set of n-dimensional column vectors with real coefficients. And the next most important example is Cn, which are n-dimensional column vectors with complex numbers as coefficients. And for most of what we do, if you just think of Rn, everything is okay. But later in the course, there are certain things that require complex numbers, and we will get to them. I've uploaded a section on course materials just about complex numbers to look at if you are not as familiar with them as you would like to be. So the most important definitions are definition of a vector space, definition of a linear transformation. So let me state this formally, and you can check that Rn satisfies all of the properties of a vector space, of course. So a vector space over the field F. So I should add a little note. What is a field? So a field is a set of scalars, set of numbers, a set. Let me just say, with the usual properties of addition, multiplication. If you have addition, you have subtraction. With the integers, you have addition, subtraction, and multiplication, but you don't have division. In a field, you also have division. And the main examples of a field are the real numbers, the complex numbers, and the rational numbers. This is the rational numbers Q, which are just fractions. So, but in general, for a vector space, you have to give a certain set and a field. And for Rn, the field is the real numbers. For Cn, the field is the complex numbers. But a vector space, so you have to specify a field along with your vector space. And a vector space over the field F is a set V, whose elements are called vectors, with two operations. One is called vector addition, and the other is called scalar multiplication. And these operations have to satisfy certain properties. And you can check that in the vector space Rn, the column vectors that by now you should know and love, all these properties are satisfied. So the first property is associativity. So for all vectors u, v, and w, if I add u plus v and add w to that, That's the same as adding u to the sum of v plus w. So vector addition is a binary operation. You add vectors two at a time. So u plus v, you can add that. That's a new vector. You can add w to it. Or you can add u to the sum of v plus w. Vector addition is commutative. For all vectors u and v, u plus v is v plus u. There's an additive identity. There's a vector 0, where v plus the vector 0, or 0 plus the vector v, is v. And there's an inverse to addition, an additive inverse. For all v, there exists a u, these are all vectors, such that u plus v is the 0 vector. And the 0 vector is unique. There's only one of them. And this additive inverse is unique. And we write the additive inverse of v, this is the vector u, as minus v. So minus v is the vector you add to v to get 0. And we define subtraction, v minus w means v plus the vector minus w. This is the definition, if you like, of this is the definition of subtraction. So all of these properties hold for Rn, and none of them should be strange. But the point is that there are many vector spaces in addition to Rn. Okay. We also have scalar multiplication. And what are some properties of scalar multiplication? First of all, for all vectors v in the vector space v, if you take the scalar 1 in the field F, 1 times any vector is the vector. Second, we have associativity of scalar multiplication. If you take C1 times C2, two scalars, and multiply that times the vector v, that's the same as taking v, multiplying it by C2, and then multiplying that by C1. And third, we have distributivity in two ways. If you take C1 plus C2 times v, that's C1 plus C2v. And if you have C times the sum of two vectors, that's CV plus CW. And it also follows that 0 plus 0, this is the scalar 0. So 0 plus 0 is 0. So for all vectors v, 0 times v is 0 plus 0 times v, because 0 is 0 plus 0. But distributing, we get 0 times v plus 0 times v. From this equation, if we subtract the vector 0 times v, we get 0 times v minus 0 times v, which is the 0 vector, is 0v plus 0v minus 0v. These cancel. So we get multiplying any vector by v, by the scalar 0, you get the 0 vector. So this is something you should definitely expect. And again, the main example is Rn. And for any field, F, we can also look at Fn, which is the set of all n tuples or n-dimensional column vectors, and each coordinate is an element of the field. And vector addition is defined coordinate-wise, just the way you know them both. What are some other vector spaces? If you take m by n matrices, so this is all m by n matrices with coefficients in R, or more generally in any field, you can add matrices and you can multiply, you can add matrices of the same size, and you can multiply a matrix by a scalar by multiplying every coordinate by the scalar. That's a matrix. We have, let's write this f of x, which is all polynomials in x. You know, polynomials are things like, look like an x to the n, an minus 1 x to the n, down to a1x plus a0, all expressions of this form, where n can be any number and the a's are the coordinates, and you just add polynomials the way you learned to do in high school. There are lots of vector spaces. In calculus, you might look at C01, which is all continuous functions, f from the unit interval to the reals. And they teach you in calculus that the sum of two continuous functions is continuous, and any multiple of a continuous function is a continuous function. Okay. So that's what a vector space is in general. You might call it an abstract vector space, though it's not that particularly abstract, but that's what it is. Now, vector spaces, oh, here, what's in a simple example, the world's simplest example of a vector space? R2, which I can write as just all order pairs xy in R. And you can draw a picture of it. There it is. Now, sitting inside R2, you might have a subset. This is my vector space R2, subset W, which all by itself is also a vector space. It's called a subspace. And we looked at subspaces already in Rn. If you have a homogeneous equation, a homogeneous linear equation, or a homogeneous system of linear equations in n variables, the solution space is always a subspace of Rn. So this, again, this is everything we're doing is familiar. Let's just give a general definition of a subspace, that W be a subset of a vector space V. So W is closed under addition, under vector addition, if whenever W is in W, in the subspace W, and little w prime is another vector in W, then the sum is in W. So W is a subset. If you take two vectors in W, the sum might not necessarily be in W, but if it is, it's closed under vector addition. What's an example of a set that's closed under vector addition? Suppose I take the line y equal x. So if I take one point, let's say x comma x, and another point x prime comma x prime, if I add them, xx plus x prime x, you add, right, this is columns, excuse me. So you have one point, xx, another point or another vector, if you like, x prime, x prime. If you add xx to x prime, You get x plus x prime, x plus x prime. So the first and second coordinates are still the same. This line is closed under vector addition. Suppose I take this line. This is the line y equals x plus 1. So a point on this, for example, is minus 1. Let's call this w. Minus 1, 0 is in w because 0 is minus 1 plus 1. And 0, 1 is in w because 0 plus 1 is 1. But if I add them, minus 1, 0 plus 0, 1, I get minus 1, 1. And this is not in w. I take this vector and this vector, and I add them, I get something over there, minus 1, 1. It's not on this line w. So this w is not closed under vector addition. This line is closed under vector addition. We also say w is closed under scalar multiplication if whenever w is in w and c is a scalar in the field, then c times w is in w. So for example, the line y equals x is closed under scalar multiplication, because if I take the vector x and multiply it by c, I get cx, and these two coordinates are the same. So the line y equal x is closed under scalar multiplication. But the line y equal x plus 1 is not closed under scalar multiplication. For example, an element in this line, if the first coordinate is x, the second coordinate is x plus 1. So this satisfies first coordinate plus 1 equals second coordinate. Y equals x plus 1. Suppose I multiply this by 2. I get 2x, 2 times x plus 1, which is 2x, 2x plus 2, which is not in w. Because 2x plus 1 is different from 2x plus 2. So this line through the origin is closed under vector addition and scalar multiplication. This parallel line is not closed under vector addition, nor is it closed under scalar multiplication. So it's nice to keep these examples in mind. Non-empty sets that are closed under vector addition and scalar multiplication are especially nice, and they're called a subspace. The subspace of a vector space V is a set W contained in V, which has 3 properties. First, the 0 vector is in W. W is closed under vector addition, and W is also closed under scalar multiplication. That's what a subspace is, and sometimes also called a vector subspace. Let's look at just another example. Suppose we take W1 to be a subset of R3 and to be the set of all vectors x, y, 0, where x and y are in R. This is a subset of R3, and I claim this is a subspace. So we have to check. First, 0, 0, 0 is in W. This is just letting x and y be 0. Second, if you have x, y, 0, and x prime, y prime, 0, and you add, you get x plus x prime, y plus y prime, 0 plus 0, which is just 0. So adding two vectors where the third coordinate is 0 gives you another vector whose third coordinate is 0. So this set is closed under vector addition. And if I take any vector in that set, third coordinate 0, multiplied by c, I get cx, cy, c times 0 is 0. So if the third coordinate of a vector is 0 and you multiply it by any scalar, you get another vector whose third coordinate is 0. So this is a subspace of R3. If you think of R3, this is R3, and the xy plane sitting in R3 is W. It's the set of all the points with z equal to 0. In general, if you have some set X and two sets, A contained in X and B contained in X. So you have A and B subsets of a set X, what is called the intersection of the sets A intersect B. It's all elements in this ambient set X, which are in A and in B. So if this is the set A and this is the set B, this part that I'm coloring in here, is the intersection. And if you have more than one set, suppose AI is contained in X, for all I in some set capital I, so this might be a finite or even an infinite family of subsets of X. The intersection of these sets, it's all X in the big set X, such that X is in the set AI for all I and I. And a nice theorem says the following. So V is a vector space, and W sub I is a subspace of V for all I and I. And the intersection of all of these subspaces is a subspace of V also. And the proof is just a verification. The zero vector belongs to every subspace. So the zero vector is in Wi for all I and I, which means the zero vector is in the intersection of the Wi's. That's the definition of intersection. If W is in W sub I, if W is in the intersection of all these sets, and W prime is also in the intersection, that means W and W prime are in W sub I for all I, which means W plus W prime is in W sub I for all I, which means W plus W prime is in the intersection of all the subspaces. So this intersection is closed under vector addition. And in the same way, if W is in the intersection of all of these sets, then W is in W sub I for all I, which means if I take a scalar C, C times W is in W sub I for all I, which means CW is in the intersection of the W sub i's for all I. So the intersection of subspaces is also closed under scalar multiplication. Okay. Again, as I always say, my writing is terrible, but that's one reason why everything is written out extremely nicely and given in the course materials. So this is the first theorem in the chapter on vector spaces. If we have subsets, not subspaces, but subsets of a vector space V, what is called the sum, A1 plus A2, these are non-empty subsets otherwise. None of this would make much sense. The sum of these sets is all vectors that can be written as the form A1 plus A2 up to A sub K, where AI is in the set A sub I, for I going from 1 up to K. And theorem 2 says the following. V is a vector space with subsets W1 up to WK, then the sum is a subspace of W. And the proof is similar to the proof that the intersection of subspaces is a subspace. We have the zero vector is in Wi for all I. So 0 plus 0, just add 0 to itself, K times. That's in the sum of the subspaces. But adding the 0 to a vector to itself just gives 0. So the sum of the subspaces contains the zero vector. And if W1 plus W2 up to WK is in the sum of the subspaces, and another vector W prime, which is W1 prime plus W2 prime up to WK prime, is also in the same sum of the subspaces. What does that mean? That means W sub I is in Wi for I, all I from 1 up to K. This is something in the subspace W1. This is a vector in the subspace W2 and so forth. In fact, Wi and Wi prime are a capital Wi. But Wi is a subspace, so it's closed under vector addition. So Wi plus Wi prime is in the subspace Wi for all I, which means if I take W1 plus W1 prime plus W2 plus W2 prime up to WK plus WK prime, that's in the sum of these subspaces. But by distributivity and, by associativity and commutativity, this is the same as W1 plus W2 up to WK plus W1 prime plus W2 prime plus WK prime, which is W plus W prime. So if I take two vectors in the sum of these subspaces, their sum is also in the sum. And similarly, C times W is CW1 plus CW2 plus CWK. If W1 is in the subspace capital W1, then multiplying that vector by C, it's still in the subspace. So this is in the subspace W1, this is in the subspace W2, and so forth. Okay. Oh, there's one kind of sum which is very useful to think about sometimes. If W1 up to WK, the subspaces of a vector space V, and let W be the sum of these subspaces, so every vector in W can be written as the sum of k vectors, one chosen from each of these subspaces. And sometimes you can represent the vector W in multiple ways. It can be written as one sum of k vectors and maybe another sum of k vectors. These vectors aren't all the same. If that doesn't happen, if every vector W in the subspace W has a unique, that means one and only one, representation in the form W is W1 up to WK, with W sub I and capital W sub I. Then we say W is the direct sum of the subspaces W1 up to WK. And the notation for this is W equals W1, and we put a circle around the zero, around the plus signs. So for example, in R3, we could let W1 be the x-axis. That's the set of all vectors x0, 0, x in R. W2, the y-axis, which is all vectors 0, y, 0, y in R. And W3 be the z-axis, with all vectors 0, 0, z, z in R. So in R3, this would be W1, this would be W2, that would be W3, and R3 is the direct sum of these three subspaces. Because every vector x, y, z is a unique representation as x0, 0 plus 0, y0 plus 0, 0, z. And there's several other nice examples in the book to think about. Now, the goal is to associate to every vector space its dimension. We want to be able to say we have a one-dimensional space, a two-dimensional space, a three-dimensional space, and so forth. I mean, Rn, we said, at least using our language, was n-dimensional. We have this column vector with n coordinates. We think of this, we say this is n-dimensional, but I want to give a general definition of dimension for any vector space. So for that, we need the notions of linear combination and linear independence. So we have a vector space V, and in that vector space, we have vectors. Let's say V1 up to Vk, and we have scalars C1 up to Ck. I can take V1 and multiply it by C1. I can take V2 and multiply it by C2. I can multiply each vector Vi by Ci. So I get these K scalar multiples of the original K vectors. And then I can add them together. And this is called a linear combination of the vectors V1 up to Vk. That's the definition of a linear combination. So a linear combination of vectors, you take K vectors, K scalars, multiply each vector by a scalar and add. That's a linear combination. And theorem 3 tells us something about one method to construct a subspace of a vector space. So let S be a non-empty set of vectors in a vector space V. The set of all linear combinations of S is a subspace of V. And it's often denoted by S with brackets around it. So S is a set of vectors. If I look at all linear combinations of them, I claim that's a subspace of my vector space, and that's our notation for it. So proof. So linear combinations are linear combinations of finite sets. So let W1 up to Wk be an S. And suppose I take two linear combinations of these vectors, C1W1 plus C2W1 to C2W2, up to C sub KWK for that W, and W prime is C1 prime W1 plus C2 prime W2 up to CKWK. What happens if I add W plus W prime? If I add and use distributivity of my scalar multiplication, I get C1W1 plus C1 prime W1, which is C1 plus C1 prime W1. And then I get C2 plus C2 prime W2 up to ck plus ck prime wk. So one linear combination added to another given linear combination gives me a third linear combination. So the set of linear combinations is closed under vector addition. If I choose all the c's to be 0, I get the 0 vector in here. And if I take this vector and multiply it by c, I just multiply every scalar by c. So if you think about this a bit, you see the set of all linear combinations of a set of vectors is a subspace. That's the theorem we needed to prove. Now, there's a very nice connection between intersections of subspaces and the subspace generated by a set S. So this is theorem 4. Let S be a non-empty subset of V, and let S with brackets around it be the subspace of V generated by S. Now, here I have V. Here I have my set S. And containing S is the subspace generated by S. Suppose I let script W be the set of all W sub I be the set of all subspaces of V containing S. So suppose this is some subspace of V that contains S. Then the subspace generated by S is in fact the intersection of all the subspaces that contain S. So what is the proof of this? First of all, if S is contained in one subspace Wi, Wi is closed under vector addition and scalar multiplication. So it's closed under taking linear combinations of its elements. So if Wi contains S, then Wi contains every linear combination of vectors in S. And it's the set of all such linear combinations is this subspace, S brackets. So that's contained in Wi for all I, which means that this subspace is contained in the intersection of all these Wi's. So that's half of what we need to prove. And You have to prove the second half. We must show that the intersection of the wi's is contained in S. But S is a subspace. The subspace generated by S is a subspace that contains S. So that means that this is, in fact, one of the subspaces Wi in this set script Wi. So the intersection of all the Wi's is contained in S. So this might require a little bit of thinking, but to understand. So this tells us something about the subspaces of a vector space and the subspaces of a vector space generated by a fixed set S of vectors. It's a very significant mention. Everything in today's lecture is significant. Linear independence and linear dependence. So a set S of vectors is linearly dependent, not independent, but dependent, if there exist distinct vectors v1 up to vk in S and scalars c1 up to ck not all zero, such that the linear combination C1, V1, C2, V2, CK, VK is the zero vector. So this means Cj is not zero for some j, at least one j. So you have a linear combination of vectors, which gives you the zero vector. Not all of these scalars are zero. That's what it means for the set of vectors to be linearly dependent. So for example, if I take V1 to be the vector 6, this is in the vector space, R2, 6 minus 14, and V2 to be the vector minus 15, 35, you can see, I hope, let's see, if 5 times V1 plus 2V2. So this is a linear combination of V1 and V2. This is 5 times the vector 6 minus 14 plus 2 times the vector minus 15, 35. 5 times this vector is 30 minus 70. And 2 times this vector is minus 30 plus 70. So that's 30 minus 30 minus 70 plus 70. That's 0, 0. That's the zero vector. So here I have a linear combination of V1 and V2 with scalars 5 and 2, so neither of them is 0. And this linear combination is the zero vector. So these two vectors are linearly dependent. And we say that a set of vectors is linearly independent the set S is linearly independent if it is not linearly dependent. So for example, in R3, if you take the standard vectors E1 to be 1, 0, 0, E2 to be 0, 1, 0, E3 to be 0, 0, 1. If I take a linear combination of them, x1, E1 plus x2, E2 plus x3, E3, that's x1 times 1, 0, 0, x2 times 0, 1, 0, x3 times 0, 0, 1. That's x1, 0, 0 plus 0, x2, 0 plus 0, 0, x3. That's the vector x1, x2, x3. And that's equal to the 0 vector if and only if x1, x2, x3 are all 0. So the only linear combination of these vectors that produces the 0 vector is the one with all scalars equal to 0, and that means these three vectors are linearly independent. Let me recall a very important function everywhere in mathematics called the Kronecker delta, delta ij. This is defined to be 1 if I equals j and 0 if I is different from j. So for example, the vector E1, which is 1, 0, 0, can be written as delta 1, 1, delta 1, 2, delta 1, 3. Because where the subscripts are different, you get zeros, and where the subscripts are the same, you get 1. And in Rn, if we let for 1 less than or equal to j less than or equal to n, if you let E sub j be the n-dimensional column vector, delta 1j, delta 2j, delta 3j, down to delta nj. This is the Kronecker delta. It's only non-zero. It's only equal to 1 when I equals j. So this is the vector which is all zeros except for a 1 in the jth coordinate. So for example, in R4, E1 is 1, 0, 0, 0. E2 is 0, 1, 0, 0. E3 is 0, 0, 1, 0. And E4 is 0, 0, 0. And you can check these vectors are linearly independent. Now, the fundamental property, a fundamental property of linearly independent vectors is that every linear combination of them has a unique expression. What that means is the following, and this is now theorem 5. In today's lecture. That V1, V2, V3 up to V sub k linearly independent vectors. If we have scalars x1, x2 up to xk and y1, y2 up to yk, so if these are scalars such that the linear combination x1, v1 plus x2, v2 up to xk, vk equals the linear combination y1, v1, y2, v2 up to yk, v sub k, then x1 equals y1, x2 equals y2, and so forth, xk equal y sub k. These have to be the same scalars in the same order. And the proof is that if this equals this, then if you, so I can write this, let me just use sigma notation. This is summation xi vi, I goes from 1 to k. And this is summation yi vi, I goes from 1 to k. So summation xi vi equals summation yi vi means that the difference is the zero vector. But this difference can be written as summation xi minus vi minus y sub I, v sub I. But the v sub i's are linearly independent. Which means the only linear combination of them that gives the zero vector occurs when every scalar multiplying the vector vi is zero. So xi minus yi equals 0 for all I, which means xi equals yi for all I. And that's what we wanted to prove, that this representation is unique. Let me just get. So now, this is my goal for today, if I can accomplish it. It's to prove what's sometimes called the fundamental theorem of linear algebra, that you can assign a dimension to every vector space. So I want to talk about bases for vector spaces. And what is the key word for today? Dimension. So this is kind of a superstar theorem. And it says the following. That S be a finite subset with m vectors in it of a vector space V. And let W be the subspace of V generated by S. Then V1 up to Vn be distinct vectors in W if n is bigger than m. So W is a subspace generated by M vectors, and I choose N bigger than M, any vectors in W. If N is bigger than M, then the set of vectors V1 up to Vn is linearly dependent. And the proof depends on the theorem about linear equations that we proved at the very end of the chapter on linear equations, systems of linear equations. So recall the following theorem. Suppose we have a homogeneous system of M linear equations in N variables. So that looks like A11x1 plus A12x2 up to A1nxn equals 0, down to the mth equation, AM1x1 plus AM2x2 up to AMnxn equals 0. So the right-hand sides are all 0. That's what it means to be homogeneous. And we prove that if n is bigger than m, then this homogeneous system has a non-trivial or a non-zero solution. That means a solution where at least one of the x's is different from 0. So this is a theorem about linear equations that we are now going to use to prove what is sometimes called the fundamental theorem of linear algebra. So what do we have? So W is the subspace generated by S, where S is a set of m vectors, and we have vectors V1 up to Vn, let's say the subset of them, contained in W. So every one of these vectors, for j going from 1 up to n, the vector Vj is a linear combination of the vectors W1 up to Wm. Because W is the subspace generated by S, that means W is the set of all linear combinations of these m vectors. Everything in W is a linear combination of these vectors. Each V is in W, so every Vj can be written as some A1jW1 plus A2jW2, and so forth, up to A sub MJW sub M. Or if you like, summation I goes from 1 up to M, A sub ij, W sub I. And that x1 up to xn, these scalars. So we have the linear combination x1 v1 plus x2 v2 up to xn vn, which I can write as summation. J goes from 1 up to n, x sub j, v sub j. But every Vj is a linear combination of the Wi's. So this is summation j goes from 1 up to n, x of j. And Vj is summation I goes from 1 up to m, aij, wi. These are finite sums, and I can interchange the order of summation. This is summation I goes from 1 up to m. Summation j goes from 1 up to n. aij xj w sub I. This is a linear combination of the w sub i's. So consider the homogeneous linear equations. Summation aij xj equals 0. J goes from 1 up to n. So this is a linear equation for all I from 1 up to m. So I have m equations in n variables. If I have a homogeneous system of equations with more variables than equations, m less than n bigger than n, there exists a solution, x1 up to xn, which is not all zero, not the zero vector. So I can find x is not all zero such that this is zero. So I have summation xi vi is the zero vector. I goes from 1 up to n, which means v1 up to vn are linearly dependent. So this is the proof on page 13 of the notes. And this is absolutely fundamental in linear algebra. It will not be surprising if to prove this theorem is a question on the midterm or the final. It really is one of the most important theorems in that course. And now we're almost ready to prove the theorem that says that every vector space has a dimension. So we say that the vector subspace W of a vector space V is finitely generated if W is the set of all linear combinations of a finite subset S of V. So there's a finite set S, and the subspace generated by S is W. So this is theorem 7. S is a non-empty finite subset of V, and it doesn't contain just the zero vector. It's allowed to contain the zero vector, but there has to be something in S other than the zero vector. And let W be the subset subspace of V generated by S, then S contains a linearly independent subset that generates W. So if S is a finite set that generates W, it may be linearly dependent, but then we can always throw away some of the elements, some of the vectors in S, and be left with a non-empty subset that is linearly independent and also generates S. So for any set X or S, let S with absolute value signs around it denote the cardinality of S, which means the number of elements in S. Or if you like, the size of S. So if I have a set and I put absolute value signs around it, that means the number of elements in the set, which is then the word for number of elements in mathematics is cardinality. Let S prime be the smallest or a smallest subset of S that generates W. What that means is that no proper subset of S generates W. Let's say S has 100 elements. Maybe there's a set with 90 elements that generates W. Maybe there's a different set with 39 elements that generates W. For every subset of S that generates W, there's a number of elements in each one. Choose the smallest number of elements of any such set S. And choose one such set and call it S prime. So S prime is the smallest subset of S. It's minimal. That means no subset of S prime generates W. And I claim that S prime is linearly independent. If not, you can find some linear combination of them. Suppose S prime consists of k vectors, W1 up to WK. Then you would have C1 W1 up to CK WK is the zero vector. And one of these coefficients will be different from zero. Say CK is different from zero. But then you can solve this equation for the vector WK. WK is minus C1 W1 minus C2 W2 up to minus CK WK. CK minus 1 WK minus 1. There's a CK here, which is different from zero. So I can divide by it. So I have S prime consists of these k vectors, and WK WK is a linear combination of these k minus 1 vectors. So if W is some linear combination, maybe I should call these A, so it's my notation. If W is some summation CIWI, I goes from 1 up to K. That's the sum up to K minus 1 plus CKWK. And for WK, I can substitute this expression. And so I only have the vectors W1 up to W sub K minus 1 on the right-hand side. This is some summation Ci prime Wi. I goes from 1 up to K minus 1, which means that the set consisting of W1 up to W sub K minus 1 generates W, which is a contradiction. Because this set has cardinality K minus 1, and we said that the smallest set that generates W, the smallest subset of S that generates W, has K elements. So this is the definition of a basis. A basis for a subspace W of V is a linearly independent set of vectors that generates W. And what we just proved is that every finitely generated subspace has a basis. And now I can finish the main theorem of linear algebra in a couple of lines. So this is sometimes called the fundamental theorem. It's theorem 8. On page 14. Every finitely generated subspace W has a basis if B1 and B2 are bases for W, then the cardinality of B1 equals the cardinality of B2. If we call this number D, D is what is called the dimension of the subspace W. Proof. Well, why is this true? So B1 is a base. So suppose we let the cardinality of B1 be M1 and the cardinality of B2 be M2. So B1 generates W, B2 linearly independent. We proved that if you have a set of M1, M elements that generates and N vectors in the set, if N is bigger than M, those vectors are linearly dependent. So if B2 is linearly independent, then the cardinality of B2 is less than or equal to the cardinality of B1. So M2 is less than or equal to M1. And then you just repeat the argument. B2 generates W. B1 is linearly independent. So the cardinality of B1 is less than or equal to the cardinality of B2. So M1 is less than or equal to M2. So if M1 is less than or equal to M2, and M2 is less than or equal to M1, this implies M1 equals M2. That's the key. So this is a fundamentally important result in linear algebra, you'll see that on the review sheet for the midterm, which covers everything that we do up to and including Wednesday. So everything having to do, so there are many problems having to do with vector spaces, linear combinations of vectors, linear dependence and linear independence of vectors, and dimension of subspaces. This is definitely a big part of the midterm. And maybe at this point I should stop because this is really a lot to think about. Again, I have problem session today at 7 on Zoom. Tomorrow, not at 7, but there's one in the afternoon, I think at 1 o'clock. And on Wednesday before the exam also. 7. Okay. Bye all.
The exam is going to be on Wednesday or Thursday?
Sorry?
The exam is going to be on Wednesday or Thursday?
No, just what's been stated all along. The exam's on Thursday.
Okay, so you're going to upload it on Blackboard and we have to do it from 4 to 6?
Yes.
Okay.